The precise definition of a limit, part 5. Now that we have the precise definition of a limit, we're going to start using it. This might be your first mathematical proof. It's not quite a proof, but it's probably more proofy than you've used math in the past. These are the general steps for using the precise definition of a limit. First, you want to state that definition correctly and completely. I won't be writing it all out in this video just because I don't think that's what you want me to do. But you want to make sure that when you're practicing, you're writing it out, which will also help you memorize it a little better. Then you want to guess a number for delta, which will require some scratch work. And afterwards, you want to show that delta works. So we want to use the precise definition of a limit to show that the limit as x approaches 2 of 3x plus 1 is equal to 7. So first, we state the precise definition of the limit. So let f be a function defined on some open interval that contains the number a, except possibly at a itself. Then we say that the limit as x approaches a of f of x is equal to L, if for every number epsilon is greater than 0, there's a number delta greater than 0, such that if 0 is less than the absolute value of x minus a is less than delta, then the absolute value of the quantity f of x minus L is less than epsilon. And we'll be using this piece here to help us create this proof. So let's get a little bit more room here. So we need to take this limit and get that last piece of our definition to apply directly to the limit we're interested in. So this is our a. This 3x plus 1 is our f of x. And 7 is the limit that we're approaching. So what we want to do is show if 0 is less than the absolute value of x minus a, where in this case a is 2, is less than some delta, then, as long as we're less than that delta, the absolute value of f of x, which in this case is 3x plus 1, minus the limit, sorry, I forgot my limit, so minus 7 is less than some epsilon. And we want to show that this is true for any delta and any epsilon. So we're not just trying to find specific numbers like before. Epsilon is just epsilon. So we have to figure something out. Well, we're trying to show that if we have this, then we can get this. So let's work backwards. We want to take this piece and transform it into this piece. Because if we do that, then we'll be stuck with whatever we're less than being a good guess for delta. So let's do a bit of scratch work. First, let's just simplify the inside of this absolute value. So we have 3x plus 1 minus 7, which is 3x minus 6. So we have 3x minus 6 is less than epsilon. And that's looking pretty close to the other absolute value that we're actually interested in. Well, let's see if we can simplify this a bit more. Maybe there's something we can factor. Well, 3x and 6 have a common factor of 3, so I can factor out the absolute value of 3. And I have the absolute value of 3 times the absolute value of x minus 2 is less than epsilon. Well, that's even closer. Well, absolute value of 3 is just 3, so I have 3 times the absolute value of x minus 2 is less than epsilon. I don't know why I wrote 3. And now I can divide both sides by 3, so I have the absolute value of x minus 2 is less than a very strange looking epsilon over 3. So I have the absolute value of x minus 2. So on the other side of my inequality symbol, this epsilon over 3 must be a good guess for delta. So let's do it. Let's guess that delta is equal to epsilon over 3. So anytime we come up with an epsilon, we can get delta by dividing that epsilon by 3, and we'll still end up with the correct inequality. Then step 3, this is all step 2, will be to actually check this. We want to show that if we have this as our delta, then we end up with this relationship still. So we want to show that if we have 0 is less than the absolute value of x minus 2 is less than delta, and the delta that we choose is epsilon over 3, so now we can substitute that in, almost wrote 2, then we get the other side. Okay, well, let's multiply by 3. So we have 0 is less than 3 times the absolute value of x minus 2 is less than epsilon. And, well, that 3 is the same as an absolute value of 3, so we can bring that to the inside. So we have the absolute value of 3x minus 6 is less than epsilon, and that's just a simplified form of this statement here. So that means we've shown that if the absolute value of x minus 2 is less than delta, and our delta is epsilon over 3, then we do in fact have this absolute value of f of x minus L is less than epsilon. And since we can just get that delta by dividing epsilon by 3 every time and still get this relationship, we've shown that this limit exists. So we've proven this limit using the precise definition of the limit. Let's look at another example. So we have the limit as x approaches 3 of 2 minus x is equal to negative 1. And we want to prove this is true using the precise definition of the limit. So first things first, we have to completely state and correctly state the precise definition of a limit. So let f be a function defined on some open interval that contains the number a, except possibly at a itself. Then we say that the limit as x approaches a of f of x is equal to L if for every number epsilon is greater than 0, there's a number delta greater than 0, such that if 0 is less than the absolute value of the quantity x minus a is less than delta, then the absolute value of the quantity f of x minus L is less than epsilon. We're going to use this piece here. Oh, I lost my if. This piece here to prove this is true for our limit. So let's get a little more space. And now let's translate our limit into that piece of the proof that we need. So this 3 is our a, this 2 minus x is our f of x, and this negative 1 is our L, the limit that we are approaching. In order to prove this is true, we need to show that if 0 is less than the absolute value of x minus a, so in this case, the absolute value of x minus 3 is less than some delta, then the absolute value of f of x, which is 2 minus x, minus L, which is negative 1, is less than epsilon. So we need to come up with some value of delta that will always lead us to this inequality. And to find that delta guess, we're going to work backwards. So we're going to take this piece and transform it into that piece so that whatever's on the other side of our inequality symbol will be a good guess for delta. So let's start by simplifying this. So we have the absolute value of, well, if we're subtracting negative 1, that's the same as adding 1. So we have the absolute value of negative x plus 3 is less than epsilon. And this looks pretty similar to the other one, but instead of having this negative x, we actually want to have a positive x. So let's factor out negative 1. So we have the absolute value of negative 1 times x minus 3 is less than epsilon. Well, the absolute value of negative 1 is just 1, so now we have the absolute value of x minus 3 is less than epsilon. So for this problem, since we now have this absolute value of x minus 3, on the other side of our inequality symbol, this lonely little epsilon here is a good guess for our delta. So sometimes epsilon and delta will actually be the same number. So we're going to guess that delta is equal to epsilon. And if everything has gone well, then when we check this guess, we'll be able to show that when delta is equal to epsilon, we can end up with this inequality. So let's go through this if-then statement. So if 0 is less than the absolute value of x minus 3 is less than delta, and we're trying to say that delta is equal to epsilon, so we can substitute that epsilon in, then this other relationship is true. And since the absolute value of x minus 3 is just a simplified version of this guy right here, because we've shown that it's just simplified, we've proven this relationship. No matter what epsilon we come up with, we now have a way to find a delta, so that if that delta is true, and we're falling within this band for delta, we'll fall within our error band as well. Let's take a look at one more linear function. So we have the limit as x approaches 4 of 2x minus 1 is equal to 7. And we want to show this is true using the precise definition of a limit. So first thing is, we have to correctly and completely state the precise definition of a limit. So let f be a function defined on some open interval that contains the number a, except possibly at a itself. Then we say that the limit as x approaches a of f of x is equal to L if for every number epsilon is greater than 0, there is a number delta greater than 0, such that if 0 is less than the absolute value of the quantity x minus a is less than delta, then the absolute value of the quantity f of x minus L is less than epsilon. And we're going to use this piece here and show that this is true for our limit in order to prove it. So let's take our limit and translate it into that piece that we need to prove. So we have the limit as x approaches 4, so a is 4, of our function 2x minus 1 is equal to 7, which is our limit. So we want to show that if the distance between x and a, so x and 4, is less than delta, then the distance between f of x, which is 2x minus 1, and L, which is 7, is less than epsilon. So we need a good guess for delta, so that afterwards we can show this if-then relationship. So in order to do that, we'll take this absolute value expression and transform it into this absolute value expression, so that whatever's on the other side of the inequality symbol is a good guess for delta. And we mostly do that by simplifying and factoring for at least linear functions. So let's simplify this. So we have 2x minus 1 minus 7, which simplifies to 2x minus 8. Getting closer there. Well, 2x and 8 have a common factor of 4, so we can factor out 4. And by 4, I meant 2. So we'll factor out 2. So we have x minus 4. My brain was getting a little bit ahead there. And then we can divide both sides by 2, since the absolute value of 2 is 2. So we have the absolute value of x minus 4 is less than epsilon over 2. And now we have this absolute value expression. So on the other side of that inequality symbol, that less than symbol is a good guess for our delta. So we will guess that delta is equal to epsilon over 2. So that means that for any epsilon we desire, we can get the delta we need by dividing by 2. And we just want to show that that's true real quick. So let's check this. So we're trying to show that, oh, I forgot my 0. If 0 is less than the absolute value of x minus 4 is less than delta, then, well, let's substitute our guess for delta in there. So the absolute value of x minus 4 is less than epsilon over 2. And then we can multiply both sides by 2. So we have 0 is less than 2 times the absolute value of x minus 4 is less than epsilon, which gives us 0 is less than the absolute value of 2x minus 8 is less than epsilon, which is just the simplified form of that inequality that we need to show. So we've shown this: if this piece is true, then this piece is true for our good delta guess. So now with all this work, steps 1 through 3, we've proven this limit using the precise definition of a limit. Next, we're going to take a look at using the precise definition of a limit with quadratic functions. It's pretty similar to linear functions, but there's like one little trick to it.